Swarm Intelligence, Ethics, and Social Implications, Iowa State University, HCI 655, Fall 2016, by Joseph Anthony Kavanagh, also known as JC, Graduate Student 2018. The focus of this project is to discuss swarm intelligence, social integration, development challenges and cultural barriers, as well as ethical concerns and social implications surrounding this technology. Swarm intelligence is the coordination of robots communicating with one another, functioning as a unit to accomplish a specific task. In terms of scalability, decision-making can be critical, particularly where the lack of control of key decisions are made as a group without human intervention. This key decision-making could have more consequences in specific industries such as in healthcare and the military. To place that responsibility in the hands of a group of decision-makers of what is considered a technology involves a high amount of risk. We need to consider the ethics and decision-making involved when developing this technology for the larger effort and greater good of human benefits. Insect robots are used to measure the scalability for how swarm intelligence can be scaled for automation across different industries. Though the concept has been around for some time, advancements in the research are continuously being made. Ethical concerns around this technology discuss where the control begins and ends. Social implications would see the loss of jobs and shifting of education practices. When we think of humans building robots, we associate the design with a human form. When we think about the creation of the anatomy of a robot, the purpose for this design is due to physical tasks we want them to perform to map our own tasks to. By contrast, biomimetic design is inspired by nature, which began animal-like anatomy, copying as the shape of the animals has its own specialty and role. Biological animals, including insects working together in groups or swarms where much can be learned and applied to our own work tasks, specifically to accomplish tasks as a group or team. Swarm intelligence, SI, includes research in both robotics and artificial intelligence, AI. It goes further into researching biology and the study of animals, specifically as groups. The study of this design, inspired by nature, focuses on behavioral characteristics and patterns of groups of animals to model artificial intelligence and systems on task-driven processes. These processes and their subjects are interrelated to one another. Researchers set up test beds using mathematical analyses, vehicle modeling, swarm architecture and synthesis to simulate biological swarm intelligence. From this they study the relationship between organism behavior and the artificial intelligence as a group or swarm. Expertise is needed from a number of professionals such as biologists, system engineers, and experts on robotics, control system theory and artificial intelligence. Swarm intelligence has been defined as an attempt to 1-2-3 design algorithms or distributed problem-solving devices, inspired by the collective behavior of social insect colonies and other animal societies. The focus is to observe natural behavior of biological aspects of swarming of bees, for example, and look for patterns in behavior on how tasks are completed. The latter part is to recreate this intelligence and map the biological tasks to robotics in a simulation. While observing biological swarms, it is important to observe which pattern movement to complete a task is consistent to map to an AI algorithm. The main parts of the application inspired by the algorithm include optimization and networks design, prediction and forecasting, and swarming robots. The purpose of studying swarm intelligence is to collect data and measure results for determining how this intelligence can scale to a much larger level where it can be used in everyday tasks for automation by a group or team inside of a workforce. The development of swarm intelligence is inspired by insect behavior. Through research and analysis, both the robotics and AI we develop for testing is our own interpretation of swarm intelligence. Patterns of emerging behavior are measured which match those of biological behavior through adaptation. As swarm intelligence continues to adapt to obstacles and challenges, tasks are learned and stored for future use, making the obstacles less of a barrier as the intelligence progresses. Whether artificial or biological, the concept behind swarm intelligence is that it is not a single entity being controlled but the emergence of a group mind. Researchers develop swarm intelligence to mimic the behavior and perception of animals. Vijay Kumar is an Indian roboticist and UPS Foundation professor at the School of Engineering and Applied Mechanics. He has developed a framework for developing swarm intelligence, mimicking the swarming behavior of animals. The method of his framework is made up of different phases: understanding biological group behavior of animals, working as a unit, analyzing the group behavior, mapping to an algorithm and running a simulation for motion and behavior, and to measure, adjust theories for engineering applications. The goal is to understand an animal-inspired engineering system and how it adapts compared to a biological system. For the actual design, researchers must model the motion behavior naturally, analyze the swarming behavior and emergent network formed and synthesize the inspiration of biological formations. The new theory of optimization algorithm can also be modeled through the robotics platform. Insects perform specific tasks, concerned only for those tasks where they use receptors which respond to pressure, light, sound, heat and chemicals. Communication of biological swarms vary, where some use chemical pheromones and others may use movement or sonar. They belong to a family and can have a number of tasks which may belong to a mode of which the agent switches itself for a number of scenarios such as danger, warning, building and collecting. All tasks are usually performed in a short period of time where they are looped or repeated until the task is complete. Memory is short and no complex calculations are being performed. The insect simply follows a specific direction for that task. In swarm intelligence, every robot is known as an agent, which is part of a unit. Each agent follows simple rules and tasks where no one agent is the leader. The outcome should have all agents performing their tasks inside a set of rules without knowing that the entire goal of the unit has been achieved. All agents must have the same capabilities, strength, speed, otherwise swarm formation will be delayed. This will not affect other agents but will result in an overall failed objective. For example, if an artificial swarm was to create letter shapes where some of the agents had greater capabilities than other agents, the letter formations may not be complete. The swarm intelligence can only be seen in the group's formation. It will not matter if the majority of the agents have great capabilities, as the deficiencies of the other agents will affect the outcome. The key takeaway to understanding and developing swarm intelligence from insect behavior is that insects are simple in and of their tasks and capabilities. They do not require complex thought or calculations. The effort to artificially replicate insects appears to be more achievable than that of creating an artificial human being or mammal. We always think in terms of creating robots in our own image to match our tasks to an artificial being. However, the effort is much greater, as it is more reasonable to recreate more simple life forms and learn from them and how they work as a unit to complete a task. The concept of strong swarm intelligence is where the computer or AI is not a tool in the study of mind but programmed to be a real mind. Biorobotic models are designed with biological capabilities in mind, as insects have capabilities such as panoramic view or response to chemical reactions. Building biorobotic models where the robot can have capabilities for environment and location in changing environments may allow for more complex tasks as well as the ability to adapt and overcome, as opposed to following a set of simple rules. Robots must deal with real input stimuli from the world in order to produce the target behavior in the real world. Strong swarm intelligence has been defined as any attempt to design algorithms or distributed problem-solving devices inspired by the collective behavior of social insect colonies and other animal societies. The collectiveness and organization of swarms is the measure of how intelligent robotic agents can be designed not only to perform simple tasks but to adapt and overcome. Collective systems which use the same control architecture can scale, as individual units can be dynamically added or removed without the need for explicit reorganization. The result is efficiency due to unit redundancy and minimalist unit design. Adaptation can be achieved quickly to changing environments or scenarios. Having a decentralized control along with clear communication methods for agents will aid systems to scale, which will allow some agents to fail and introduce new ones. The use of biorobotic models means that we could achieve and perform real tasks in the physical world. In regard to social integration, experiments also measure the possibility of integrating robot agents with biological animals, where artificial agents are modeled to interact and to work autonomously with animals, biological insects, and other robot agents. Designing these models would account for capabilities to include sound, visual cues, and social organization. Identifying individual behavioral algorithms can replace some of the biological animals with robot agents to compare collective responses in mixed and natural groups. The purpose of these experiments to understand the scalability for the integration of robots and systems into the human workforce. We simply cannot replace all humans with robots and AI at once. It will be a gradual integration to working collectively for the greater effort. As with many new technologies, there are key challenges in the design, development and research for swarm intelligence. Although these barriers are common with most new technologies, they are worth mentioning to set expectations of why this technology is not already a reality. The cost of the robots and robotic parts is a major barrier. Creating simple small robots for testing pales in comparison to creating robots that actually build things when it comes to cost, particularly sensors, cameras and motors that make the robot function. In addition, the engineers and technicians who build robots do not come cheap. Also, robots have difficulty solving problems on their own, and there is a lack of coordinated algorithms and applications which are necessary to exchange critical information very quickly and accurately with one another. Also, robots must communicate with each other directly, in addition to communicating to the internet. Finally, there is a general fear from the public. Not everyone is on board with the robot revolution, especially those whose jobs would be at stake. The technology would quickly replace those who do repetitive and menial work. The public may also have a general fear of robots and AI systems who are capable of important decision-making as well, because the concept of swarming revolves around independent parts which are linked together making up a swarm. There is no leader or central unit. The swarm self-organizes and adapts, making decisions and adjustments for the overall arching goal. How this applies to swarm intelligence means each system would be given a few operating orders and be let loose, each robot acting on its own, but also in collaboration with all the others. The idea of scaling swarm intelligence brings up many concerns. Everything from loss of life, to safety, to concerns for protocol. For example, imagine a military unit running itself, taking a life of its own with key decision-making. Human intervention needs to drive the intelligence, as our dependency can only go so far. If we depend more on swarm intelligence to make key decisions, risk becomes greater. This risk needs to be addressed by a number of practices and institutions, including technology corporations, lawmakers, medical professionals, scientists, engineers, military officials, as well as ethics committees. Special interest groups would rise in opposition to swarm intelligence and robotics for a whole host of reasons. If we assume that military robots are single autonomous agents which perform military tasks, it is the absence of human control where great risk lies. It is not enough to think of them as single entities but larger systems, networks, and swarms. Drones as killer robots are operating under human control. To put this control inside of a group of robots with minimal human intervention opens up many ethical concerns regarding where the control begins and ends. However, it is possible that measuring this may only be achieved through testing and eventually real-world use. As with many emerging technologies, feedback can be collected and improvements can be made, but at what cost? In the healthcare industry, medical professionals could be replaced by robots and AI systems. This could start as simple as collecting patient information to more advanced tasks such as medicating to the end of the spectrum of surgical procedures. However, as with the military, the risk lies in swarm intelligence being independent or having minimal human intervention where control is handed over. The idea that a swarm of medical units tasked with helping humans would require not only sensitive adjustments but the ability to learn and adapt to real-life threatening situations. The concept of roboethics is how we apply our own human ethics in the design and development of robots and IA, including swarm intelligence. However, even if we design within these boundaries, the idea of a robot or swarm having the ability to learn and adapt as a unit could produce unpredictable results. Before we even take into consideration placing control and ethics, we must define what is meant by ethically sound and acceptable behavior by a robot. A major impact of swarm technology could be the replacement of humans in the workforce. We had previously discussed social integration for how robots would be integrated inside of a work group or unit. Over time, this could be fully implemented in certain industries for task-driven jobs. The work environment could be transformed with a workforce we may not recognize as technology quickly changes and becomes more developed. There still will be developmental challenges as well as ethical concerns as we had previously discussed. However, implementation could happen in stages over time as new generations become more accustomed to an AI robotic service industry and workforce where cost is reduced. There could also be cultural barriers where certain cultures and religious beliefs may never want to adopt a form of robot technology, let alone swarm intelligence. In the evolution of human needs, cultural barriers will always be a challenge. However, every time humans have fought technology, technology has always won. Much of this is due to technology being infinite and progressive, where we as humans die off and a new generation of humans are in play to accept new ideas, especially if technology has played a big part early in their life. Another implication could be education. If swarm intelligence is used in the future, it could reshape education curriculums where certain degrees or vocational skills would become obsolete. Education will always be important, but the shift into what is viable will be pushed by technology. Today, many college grads already find themselves struggling to find a job, not specifically due to a downed economy but because there is simply not enough demand for those jobs, or they are moving more toward automation. In the future, more careers may disappear or perhaps shift toward other disciplines. One example in a higher skilled area could be nursing. Another example in a lower skill could be freight and cargo loaders working autonomously for more accuracy and lower cost.